parallel. They're parallel to each other.
Mr. Davis, that's what we said. You said no.
You said series parallel.
No, said parallel.
Okay. Oh, I'm sorry. I must be losing. I could swear I heard series parallel. I'll play the recording back. But yeah, okay, you said parallel. That's what it is. It's parallel. Okay, let's see, can we figure this out? Alright, so this is what kind of circuit this is?
This is parallel.
Close. Not exactly, but you're close though.
Series?
No. Look at this.
Parallel?
See this right here? That's a parallel circuit. It's more. Remember, it's more than one branch. I can go this way, the ground, or I can go this way, the ground. That makes it parallel. They're parallel to each other.
Mr. Davis, that's what we said. You said no.
You said series parallel.
No, said parallel.
Okay. Oh, I'm sorry. I must be losing. I could swear I heard series parallel. I'll play the recording back. But yeah, okay, you said parallel. That's what it is. It's parallel. Okay, now, what I want you to do is, see, can we find the amperage here in this circuit? It's two ways of doing it. All right, it's an easy way, and then you can do this. R1 times R2 over R1 plus R2 equals the total resistance. I don't know if it's TR or RT. That equals your resistance, the total resistance. Or you could do the simpler way by making each one a series circuit. Let's see what answer I get for this. Go ahead and try it and see what answer I get.
Should we say it out loud?
Yeah, if you got it, yeah.
3 amps?
Okay. Anybody else? Get anything else? Anybody get anything else? Okay, y'all agree. What you get? What you say?
3.
Yes, 3. Now, how did you get to 3?
100 over 20 equals 5 ohms. 5 ohms times divided by 15 equals 3.
Right. That's a way you can do it also. Right. You could do. I'm assuming you did it like this. Hold on a second. I'm assuming you did 10. So you're saying 10 times 10 over here. Then 10 plus 10. Oops, that's wrong. Equals 100 over 20. No. So all we're doing is taking these two, R1 and R2, and sticking it here. Okay. Now, it equals obviously 5. 5. Alright. So now that's my resistance total. Now what I want to do is take, remember we're still doing this. And remember, sometimes I put an A there, but that's just me. We're still doing this, so now we want to find the resistance. Okay, and how to find the resistance is voltage divided by amperage gives me resistance. All right, so I'm gonna take this 20. I'm gonna take this 15 volts and divide it by. Oh no, I said that backwards, didn't I? All right, so it's voltage divided by resistance gives me amperage. I'm sorry, I said it backwards. So what we're going to do is take the 15 volts, which is this, divided by my resistance, which is this, equals 3 amps. So remember, this 5 is my resistance total. I'm just taking that and dividing to the voltage.
You could also do it one by one and then just add them together.
That's the harder way of doing what I just did. But now, the much easier way. Now, see, in some cases, you're going to need to know that, though. Okay, I'm gonna show you in a second. You're gonna need to know how to do this. That's why I've shown it to you. So the easier way of doing it, if you can, is do this. If I want to find an amperage, what's the rule? What's the rule of amperage in a parallel circuit?
Voltage the same. The same.
Well, the voltage is the same. Yes, that's true. How about the amperage?
The amperage is supposed to be for each side and parallel.
Yes, the amperage to each branch depends on the resistance. And also the other rule is the total amperage equals the amperage that left the battery. So for instance, remember we're still doing this rule here. We're still doing this formula here. Remember, we're still doing this. Okay, we still have that in mind. So I want to find an amperage in branch 1. This is branch 2. Okay, so what I want to do is I want to treat each one like a individual circuit. So I'm going to take 15 volts divided by 10 ohms equals 5 amps in that branch. So what I'm saying is, in this branch number 1 is taken up, is using 1.5 amps. Okay? It's using 1.5 amps. So obviously the next one, number 2, here, obviously going to be the same number because it's 10. You do the same formula here, and this one's going to be using 1.5 amps. So what leaves the battery to do the work is 3 amps. And what goes back to the battery is 3 amps. But all we did was add them up on the parallel circuit. So whatever leaves the battery, right, does the work. And since a parallel circuit, they're added up.
Mr. Nate, I have a question. This is Eric.
Yes, Eric.
So say for example you would have another branch making it 3 resistors. Would that formula that you have on top, would that still work?
Like that?
Yeah.
Now which one are you talking about? The first one I did, R1 times R2, or R1 or the individual branches? This one.
R1 times R2.
Yeah. Now you got yes, that's a good question because R1 times R2, you have to do this. Either way, you don't have to because it's not a series parallel; it's just a parallel, right? But you could do it on. You can. Now on this one, I take that back. On this one, you can do individual branches also. The next one, you have to do R1. Next one, you have to do R1 times R2. I take that back. If it's a series parallel, or if it's a series parallel, like let me show you. I can answer it this way. If I had this. I hope I'm answering this correctly for you. If I had this is a series parallel, right? Now, this making an individual series circuits, like we just did the second one we did, this one, it won't work here. And the reason why, because that's in the way. Okay? We have to calculate, we literally have to calculate this first. Right? And our problem is, we want to make this one circuit, not a problem. We want to make this one circuit this. You will make this circuit, that circuit, to get the total amperage in this circuit. For example, let me show you. Now we can't make them individual series circuits like we did the last one. So we would have to do the R1 times R2 formula. And you always do the ones in parallel first. So it'll be 2 times 2 over 2 plus 2 equals 4 over 2. My resistance total would be what?
It's 4 over 4, Mr.
4 over
4.
4.
I'm sorry. That's a quick, though. My math is off. 4 over 4. I'm sorry. My resistance total would be what? 1, right? All right. So now this one branch, my total resistance is 1. It's 1. So now I would have 12 volts, 2 ohms, and the answer to this was 1 on here.
Yeah, that's more clear, Mr. Nate. Thank you.
So we finished this. Okay, that's good. Now we finished this one, right? Make this a total resistor. You got 2. Oops. Oh, I finished this. You had 2 and 1. Our total resistance was 3. You may take out the way. That's 3. Now we figure out 12 volts divided by 3 ohms is 4 amps in this circuit. We did all that just to get to this circuit here to get the amperage. So once you got the amperage, you don't need that no more. So now we know the circuit's 4 amps in that. Now we know it's 4 amps in that circuit. I have a question for you. Since this is a series parallel circuit, do these two circuits still drop 12 volts? Remember the rule in the parallel circuit. They should drop source voltage. In this case, do they drop source voltage?
They split 12 between each other, 6 each.
That would be the correct answer if that wasn't in the way.
If that wasn't there, of course.
Right? If that wasn't there, sorry, I'm sorry.
2 volt each.
If that wasn't there, I should say, you would be right. Because remember, Robert, what we have right here is a resistor in the way. So we're going to have to drop the voltage across that first. Then whatever left over is going to be at the parallel side.
Right. So we have, I think, 8 volts right there.
Exactly, Robert. That's exactly right. You
And
have
we
8 volts here. That means on the parallel side, we're going to have what?
2 each.
No, almost.
4 each.
4 each, exactly.
As the voltage stays the same.
Exactly. Now it's parallel, it stays the same. And what Robert just showed you was, this is 4 amps times 2 ohms equals an 8-volt drop. So this one resistor here, this one resistor used up 8 volts. So now what's coming out of it, once it used up the 8 volts, remember, it's 12 going in, it used up 8, what's coming out is 4. So now since this is in parallel, they're going to share that 4 volts. So if that was a set of lights that's supposed to get 12 volts, what would happen to the lights or the motor? What would happen to it?
I'm sorry, what was the question again?
If this was a set of lights, let's say these were light bulbs right here. This one and this one were light bulbs. And it's supposed to get
down.
Yes, it would be dim. And it's supposed to get 12 volts. Now they get 4, they would be dim. Now this is how you use Ohm's law. Remember, Ohm's law, we don't use the math, we use the concept. Okay? Now let's say that's a set of light bulbs or a set of lights, right? And they get 4 volts. And let's take this resistor here, that resistor. Let's take that resistor and make it a switch. Now, technically, if you engage the switch, you get 12 volts, right? Because it's just a switch. I shouldn't lose nothing. Unless we had crud. Unless we had crud on the switch. Now we have a problem with the lights. You see, I just took Ohm's law and applied it to a practical circuit. Remember, we don't use Ohm's law in the car like this, but we use that same concept. Use that concept. I'm going to cross a set of lights. I'm reading 4 volts. Something's wrong. You should know you got resistance somewhere in that circuit. And you find it by doing, what's that term called? It's on the test. Make it more interesting. What's this term called when you do this?
Voltage drop.
Voltage drop. Thank you, Ricky. Called a voltage drop. Sorry, Eric, that's a long answer for your question.
That was really helpful.
You know what? Just went off on a tangent there. Now let's go to this one. Now this is going to be a little bit more difficult. This is going to be a little more difficult. Alright, now